Hey everybody, in this AP Chem series video, we're going to take a look at the differences between strong and weak acids and bases. First, remember that so far we've described acids and bases using the Arrhenius theory, the Bronsted-Lowry theory, and we've talked about the pH scale that measures acidity by looking at the quantity of H3O+, and all that means that it's time to move on and talk about this term acid and base strength. The first thing to clear up is that the word strength, or strong versus weak, is actually a confusing term when you hear it. If, let's say, you were talking about a strong acid or strong base, the word strong kind of makes you think that that's going to be an acid that is dangerous or corrosive, reactive, or maybe even more concentrated, and it just doesn't mean any of those things at all. A good example of this is hydrofluoric acid, termed a weak acid, and yet it's one of the most dangerous and reactive chemicals known to man. If you've ever seen the TV show Breaking Bad, they actually used it to completely react away and cover up a dead body, and it's so corrosive it burned right through the bathtub and the floor itself. The terms strong and weak really only describe one thing, and that thing is called the extent of dissociation, and we're going to start this video by talking about that. So this word dissociation comes up a lot in chemistry, and anytime you see it, it's just describing a process where a compound breaks apart into smaller pieces. Usually it's describing atoms that are separating from each other. In terms of acids and bases, they're going to do this by ionizing and undergoing that hydrolysis reaction when you add them to water. So in the case of an acid like HF, we know that hydrogen is going to move over here and attach to the water. We can now say that hydrogen is dissociating away from the fluoride. That dissociation allows us to produce the expected H3O+ and F-. If I was going to model this, I could add maybe 4 HF molecules. The weird part is that if I'm drawing 4, it's really only 1 out of those 4 as an approximate percentage that's going to do this dissociation. And that's because in the case of HF, it's actually more stable to have the hydrogen still attached. So that's what most of them are going to do, a very small percentage break apart. This is something known as partial dissociation. If instead we had a different acid like HCl, it's going to dissociate in the same way, but the amount that it does it is different. If I add those same 4 HCl molecules, in this case all 4 of the molecules will dissociate and produce those H3O+ and Cl- products. Almost none remain attached, and that's because it's actually the product Cl- that's the more stable form, so nearly all of them will do that. This is called complete dissociation. And all of this leads us to the definitions or ideas of what strong acids, and this is going to apply to strong bases too, of what that actually means. The term strong means that acid or base will experience complete or nearly complete dissociation when in an aqueous solution. These hydrolysis reactions are reversible, so there is an equilibrium that's going to be formed here. But the good news is that the K values, the equilibrium constants, are so insanely large that we kind of ignore the fact that they're reversible altogether and just pretend that they actually just go in one direction. They just go to completion. So you can even see the arrow here is forward facing only. And the point of that very, very, very large K value, and what that tells us again, is that there's essentially no HA left. It's all dissociated and turned into H3O+ and A-. On a molecular level, what's really happening here is you've got a pretty weak bond between that hydrogen and the rest of the acid, so it's very easy for it to break off, so most of them and all of them do. Another way to think about it is that the conjugate base, that A-, is the more stable form. These make up some of the key ideas for this video. Make sure to pause and take some time, write those down. That leads us finally to weak acids and bases, which are the other scenario. These guys are the ones like HF that experience partial dissociation. The hydrolysis reaction is the same as it always is for any acid or any base. It's also reversible, but this time it's extremely reactant favored. So you can have very, very small K values, much, much less than 1. Small Kas for acids, and same thing with weak bases. You're going to have very, very small Kb values. In both cases, that small k tells us that there's very small amounts of products being formed. On a molecular level, this correlates to a stronger HA bond, at least for the acid form. So that means most of the H's will stay attached to the rest of the acid. or the conjugate form. In the case of acids, the A-, or bases, the BH+, that's actually less stable, so you end up with less of those products. These make up some of the final key ideas for this video. Make sure to pause and take some time and write those down too. That also wraps it up for this video on strong versus weak acids and bases. Thanks a lot for watching, and here is a brief summary.